All right, today we are going to be talking about section 6.5, the trigonometric form of a complex number. So the idea here is we're going back to complex numbers. Remember, complex numbers involve I. Remember, I stands for the square root of -1, although we're not going to be using that a ton today. All complex numbers can be written in the form a plus bi, and you may have graphed complex numbers in the past. The complex numbers work just like coordinates. When you have your a plus bi, when you have that point, well, you're just going to go over to a and up to b, and that would be the point on the complex plane. Something we haven't done very often, but it does come up a little bit in this section. So what we can do is there's a formula for the absolute value of a complex number. Because you're finding the distance from 0, 0 to AB, it's essentially, the reason this comes up, it's our formula for R that we've been using all along. So you can find the absolute value of a complex number. It's no different than finding R, a squared plus b squared, and you take the square root of the whole sum. So this next slide should be relatively straightforward. If you were to graph this on the complex plane, it would be 2 to the left and 5 up. That's where it would graph to. So they are essentially thinking, what's the absolute value of that? We want to know essentially its distance. And it's no different than -2 whole quantity squared plus 5 squared, and we take the square root at the end. This would be the square root of 29. And that's the distance from this point to this point. That would be the distance of the square root of 29. It's always going to be a positive answer. R is always positive. That's why absolute value there, also positive. Okay, so really getting into where is this going is the trigonometric form of a complex number is, yes, we can write all of our complex numbers a plus bi, but there's a second way to write it. You can write it more defined by an angle measure and the radius. And the way I would look at that is, so let's say we have any point out here, AB. What we do know is we could make this a right triangle. And that way we would know this is A, and we know this is B. And we have ways to actually, and we call this angle here theta. We've done that for most of the year. We have ways to represent. If I think of this as a right triangle, I could say that cosine theta would be equal to adjacent over hypotenuse. A better way of saying that is r cosine theta is equal to a, because all I'm going to do is multiply both sides by r. All right, so this is one of the important statements. We now have a way to relate a to theta and r. Similarly, we could use sine theta to be the ratio of opposite over hypotenuse, b over r. And an even better way to write that, if I multiply both sides by r sine theta is equal to b. So now I have a relationship. I know I can figure out b, I can figure out a. I have a relationship with r. As well, I also can figure out, if I know a and b, I know that tangent theta is equal to b over a, opposite over adjacent. So I now have 3 very important, and in fact, if you take the absolute value from the other slide, 4 very important relationships, that fourth relationship being the a squared plus b squared. These 4 relationships are really going to be the foundation of this section and going from trigonometric form to complex form. So in this diagram, I hope you can see that a is equal to r cosine theta. I would say the same thing goes for b. Those are 2 important parts. So if I know a and b, I have enough information to figure out r and theta. What you're going to be able to do, if you have a complex number written in the standard notation, well, then you could use that information. You could use tangent theta is equal to b over a. That's going to get you theta, because you could use tangent inverse. So now you'll have theta. You can also get r by doing the square root of a squared plus b squared. And you can plug it in. Once you have both of these pieces of information, you can plug these into here and into here, and you will have a trigonometric form of a complex number, and your trigonometric form of a complex number is going to look something like this. The only thing that they've done is they factored out the r, where over up here, I didn't necessarily write that because it's two separate equations. All right, so these four pieces are really the foundations of transforming from trig form to just a regular complex number, standard form. All right, now you don't hear these used too often. All right, but r is and theta are two new terms in terms of this complex, the trig form of a complex number. R is called the modulus of the complex number, and theta is called the argument of the complex number. Those are more just definitions. You'll see them every once in a while. Okay, so here I have a complex number, and I want to write it in trig form. So what I need to find out is I need to really figure out r, and I need to figure out theta. And if you want to do r is the straightforward one. It's the one we've used before. It would be -2 squared plus -2 radical 3 squared. When I do that, 4 plus, now we got to be careful, -2 squared is 4, and radical 3 squared is 3, so I still need to multiply that. I'm total getting radical 16, which is 4. So r is 4. What I need now is to figure out theta. And the way I figure out theta is by using the fact that tangent theta is equal to b over a. So I know tangent theta is equal to b is -2 radical 3 over -2. Now you notice those -2's are going to cancel right out. And what I really have is tangent theta is equal to radical 3. Now, we should be able to figure where that happens on the unit circle. So we should be able, so we know that theta has to equal pi over 3. Now, you got to be careful here, because pi over 3 would indicate that this point right here, a comma b, is in quadrant 1. I would hope you know that is not in quadrant 1. That has to be in quadrant 3, because both a and b are negative. So, the reason that this answer is not in quadrant 3 is because tangent has a period of pi. And we would need to know to get that into quadrant 3 where we want it, we'd have to add pi, making our real theta value 4 pi over 3. Okay, so how do we turn this into a trigonometric form? Well, we already know r. R is going to be 4. And what you can do, we write our a term first, which is just going to be cosine of 4 pi over 3 plus I sine of 4 pi over 3. All right, these angles will always be the same. You're getting those from here. This 4 is always found the same way we have found we found r in the past. And then it's just a matter of plugging it into the formula. That's your trig form. If you distribute the 4, I'm perfectly okay with it. Either form is acceptable. All right, so that was writing in trig form. Now let's take trig form and go back to standard form. All right, so in fact, I actually think this method is easier because all it really revolves upon is we should know the cosine of negative pi over 3. So, so to be able to solve this, it's radical 8, parentheses, the cosine of negative pi over 3 is 1/2, yes, plus I, and the sine of negative radical 3 is the sine of negative pi over 3 is negative radical 3 over 2, and all we need to do is a little bit of a distributive property, and you would get radical 8 over 2. I'm going to write down minus, only because that's getting rid of this this negative sign here, and you could call that the square root of 24 over 2, and then you don't forget the I. The last part that needs to happen here is you need to simplify your radicals, so I would call that 2 radical 2 over 2, because simplifying radical 8, minus that would be 2 radical 6 over 2. And this really is just radical 2 minus radical 6I. If you were to try to go back, you could actually take, so this is your standard form. Right here, this is your standard form. If you want some extra practice, you could put this into trig form using the process from the previous slide. You know, finding r, which, you know, if you were to square this and square this, and add them, you're going to get radical 8. And then you should be able to get the pi over 3 by doing b over a. You'd see tangent theta equals b over a. You should be able to get negative pi over 3, or that's the same as 5 pi over 3. So you have a couple different options, but it's good practice. All right, so next up, there are some properties to multiplying and dividing complex numbers that, when they are in trig form, make it extremely easier to multiply these numbers. So what we're going to have for these two formulas, Z1 and Z2, that's what they're going to be defined as. These are both in trig form, right? Both Z1 and Z2 are in trig form. And to multiply in trig form, you really just multiply the R1s and you add your thetas. And everything else stays the same. Multiply R1 and R2, add theta 1 and theta 2, and you're still going to have cosine of a new theta plus I times sine of that same new theta. The difference when you divide Z1 by Z2, well, instead of multiplying your R's, you're now dividing your R's. Instead of adding your thetas, now you subtract your thetas. And that's exactly what this last theorem is stating. Right. So if you need to take a second, pause, take those down into your notes. On the next couple slides, we will be using them. Find the product of Z1 and Z2. Well, if you think back to the very last slide, what needs to happen, these two numbers need to be multiplied. That's where I'm getting a 16 from. All right. The theta values need to be added. So somewhere I need 2 pi over 3 plus 11 pi over 6. So I need to get a common denominator. So 4 pi over 3 plus 11 pi over 6. That's going to be 4 pi over 6, sorry. 4 pi over 6 plus 11 pi, that's going to be 15 pi over 6. We can reduce that to 5 pi over 2. And if you want to make it even easier, you could use a coterminal angle. Pi over 2 is the same as 5 pi over 2. So now that I have multiplied the r's, 2 times 18, I got my 16. That's my r. All I have to do is cosine pi over 2 plus I sine pi over 2. It's as easy as that, multiplying complex numbers. We will do one more division, and division works exactly the same way. Here it's in degrees, so it's actually even easier. I need to divide my r's, so 24 divided by 8, that's where I'm getting the 3 from. I need to subtract my thetas, 300 minus 75. Well, that's going to be cosine of 225 plus I sine of 225. And that's every division problem. It's division. Divide your r's, subtract your thetas, and you are done. All right, we will be working on powers on the very next slide, and we'll do that in our next video.